Welcome to another video on the iGetChem channel where we help you learn chemistry the easy way by showing you how to solve problems. This is another video in our quantum chemistry series, but this is a new one in a new segment that's called Examples of Quantum Systems. In a typical course in quantum chemistry or quantum mechanics in chemistry, typically, there are applications of the principles of quantum mechanics on specific example systems which relate to molecular systems that are commonly found in chemistry. And so typically these are these examples that are typically addressed in quantum chemistry would be particle in the box, the harmonic oscillator, the hydrogen atom, angular momentum, and things like that. So this first problem that I have selected is on the particle in a box problem. And let me read the problem first, and we will go straight to the solution. So the problem is asking you to calculate the probability of finding the particle in a box problem in the region between L over 4 and 3L over 4. Okay, so the way your book formulates the particle in the box problem may be different, may have different parameters, but basically the solution boils down to the same thing in every book. So I'm going to try to just quickly go over what this is, and then we can look at the solution to the problem. So this is the particle in the box problem in 1D. So typically in the particle in the box problem, you have an otherwise free particle, but it's confined in the interior of a box. So to try to sort of represent that, I'm going to use two walls to represent the boundaries of the box. So we put a wall there and a wall there, and the particle cannot penetrate into these walls. So these regions on the outside, they are the forbidden regions, and the particle is only allowed to be found inside the box. So inside the box we have, let's say, a coordinate system which we will call x, and we can simply assume that on the left side it is 0 and on the right side is L, and L is therefore the length of the box. So inside this region, this is the allowed region. So whichever solution you find for the particle in a box problem, the wave functions must vanish at the walls and beyond the walls. So as we have said, the particle in a box is basically a free particle that is trapped inside the box. So the only term in the Hamiltonian for a particle in a box problem is in fact just the kinetic energy operator. And so that's equal to p squared over 2m. And of course, in quantum mechanics, the momentum operator becomes minus IH bar times partial x if it's in one dimension. And so this is over 2m, but then on top, this is going to be a squared. So it will come out to be minus h bar squared over 2m. Because it's in one dimension, I'll just write d squared by dx. So, and that is in fact the only term in the Hamiltonian. Okay, so the time-independent Schrodinger equation for the particle in a box problem then simply becomes minus h bar squared over 2m d squared dx squared times psi of x is equal to E times psi of x. So this is the eigenfunction, eigenvalue problem that we need to solve. So this is fairly simple because we know that the functions that solve this differential equation are going to be sines and cosine functions. So the first one is going to be a function that looks like that, because the function must satisfy the boundary conditions. Each of these solutions to the Schrodinger's equation will have to basically go to 0 at both endpoints. So it's 0 here, as 0 there. So this is going to be essentially 1/2 of a sine function. You know that the sine vanishes on 0 and pi and 2 pi and so forth. So this function would satisfy the boundary condition, and this is simply a sine of pi x divided by L. So we will call this psi of n equals to 1. And so you can basically see that the other functions are also fairly simple. So let me draw another one. Draw a line here again. And so I'm going to draw the next one. The next one is going to have a node right in the middle. So I'm going to represent this node by a blue dot right there. So again, this wave function must vanish at both endpoints. So the next one that would actually fit, which is a sine function, will look like that. So that's the second one. And clearly you can see that the functional form of this next one is just sine of 2 pi x over L. Okay, so I'll call that psi 2. And you can easily imagine what the next field would look like. Let me just do one more. So the next one will look like this. Again, it would vanish on the walls, but it would now have two nodes, 1/3 of the way and 2/3 of the way. And now that wave function would look something like this. So this would be psi 3. And so the functional form of that function would, of course, be sine of 3 pi x over L. And that's called psi 3. Okay, so continuing on, what we can do is to then plug these into the Schrodinger's equation to find out what are the corresponding eigenenergies for each of these states. Now, the problem doesn't ask you to do that, but I'm going to do this quickly to try to illustrate some key points. But before I do that, I'm going to try to change these wave functions by using a transformation of coordinates, so that instead of x going between 0 and L, I'm going to transform that into a new coordinate y. So in this case, x is between 0 and L, but after the transformation, I want my y to go from 0 to 1. And so you can easily see that if I define y equals to x over L, then the value y would be between 0 and 1. And that just makes the mathematics a little simpler. So let me just do that. So if I do that, then you see that the first wave function, psi 1, which now is a function of y, is going to be just sine pi y. And the second eigenfunction, psi 2, is going to be sine of 2 pi y, and of course psi 3 is sine of 3 pi y, and dot dot dot. There are many of these. So collectively, I can rewrite all of these as essentially psi n, where n is 1, 2, 3, or any other integer. So psi n of y is equal to sine of n pi y. Now at this point, there's something missing from these psi functions, which is even though these are the correct functional forms of the solution, they are not exactly correct because there has to be a normalization constant in front of every one of these. So the first one I'm just going to call C1, second one C2, C3, and C1, C2, and C3 might be different for every one of these eigenfunctions. So to be complete, the eigenfunction psi n could be written as Cn times sine n pi y. So to determine what these normalization coefficients are, we will have to do an integral. The reason why they are called normalization constants is because these wave functions have to be normalized, and so for them to be properly normalized so that the integral over the square of psi comes out to be 1, you will need to find the right normalization constant to make that come out correctly. So before I do that, maybe let me just draw what the square of psi would look like before I actually do the integrals. So again, I'm going to draw the walls. And I have the right one. And now in the in this dimension, instead of having x, I have y, and now y is between 0 and 1. So I am going to take a look at this wave function psi 1 of y. You remember psi 1 of y is basically just half of a cosine function. But what I'm going to do is I want to plot the square of that because it is the square of the wave function that represents the probability of finding the particle. And this is the what this question is concerned with anyway. So let's draw the square of psi. So if you take that cosine, the square of that would look something like that. I didn't do a good job, but so it would look something like that. And if you take the second one, that one would look like this. In this case, again, we remember there is a node right in the middle. So if you take that function psi 2 and you square it, it would look something like this. Clearly, once you square the psi 2, it becomes a symmetric function. And so this is psi 2 of y squared. And let me just do one more. So this one is psi 3. In this case, it has two nodes, 1/3 of the way for the first one and 2/3 of the way for the second one. And now you see this, once you square it, you will get something like this. So there are basically 3 humps here, and they are evenly distributed. So this is psi 3 of y squared. And now what you want is to make sure that the coefficient in front of these wave functions will help the integral of psi 1 come out to be equal to 1. So the requirement for the normalization is the integral over psi 1 squared in the entire region will come out to be 1. And similarly, you want all of these integrals to come out to be equal to 1 for every one of these eigenfunctions. So let's just write down one of them, and the other ones are going to be fairly clear. So the one for psi 1 is this one. So this one. So I'm going to write this integral down. This is basically c1 squared times the integral dy from 0 to 1 of sine of pi y squared. And that has to be come up to equal to 1, so we can now fix the value for c1. So you can easily figure out what that integral is going to be. This is just a sine squared, and you can do the integral. You can either look up an integral table or do it yourself, and you can easily figure out what the value of this integral is. I'm going to do it a lazy way or by a slightly different way to try to illustrate a useful technique. I know, for example, sine squared of anything plus cosine square of the same thing, of the same argument, must be equal to 1. So if I look at this function, which is sine squared, then if I look at cosine squared of the same argument, so instead of looking at sine of pi y squared, if I look at cosine of pi y squared, it looks exactly the same, but it's just shifted from the boundary. So so what I mean by that is if I plot this function would look something like this. So instead of starting at 0 and going to 0, going to 1 again, it would actually start with 1 at y equals to 0, and then would go down to 0, and then would go back up to 1. So that function would look something like that. Now, of course, if you look at that function and you cut it in the middle, so you take a cut right there, you see that whichever is on the left side of the area under the yellow curve is exactly the same thing as what is on the right side of the yellow curve. And similarly, if you look at this original sine square function, this one right there, you see that whichever is on the left side must be equal to whichever is on the right side. These two halves are the same. And because sine and cosine have to add up to be equal to 1, which is, so if you add the sine square and cosine square have to add up to be equal to 1, then if you add them up, the total is that. So clearly, the integral of 1 over this entire region is just 1 because the y range goes from 0 to 1. The height is just 1. And so the integral is just equal to 1. But that is equal to the integral of sine squared plus the integral of cosine squared. But the integral of sine squared and the integral of cosine squared are the same because the areas are the same. So the sine square integral would be necessarily just 1/2 of 1. So even though you can look up this integral, you can easily do this by understanding that whichever you get is just 1/2. And so once we see that c1 squared times 1/2 must be equal to 1, you can clearly see that c1 is going to be equal to square root of 2. Okay, so that helps us nail down what the normalization constant is for psi 1. And in fact, you can carry out exactly the same argument for all the other wave functions. Again, using the same symmetry argument with sine squared and cosine squared summing to 1 inside the region of integration, but the sine square integral is exactly equal to the cosine square integral. So you would find that for every one of these C1 coefficients, for every one of these Cn coefficients, they are all actually equal to the same number. So you'll find from this one that C2 is equal to square root of 2, and C3 is equal to square root of 2, and they're all the same. So there's really no difference between these. They're all the same normalization. So going back to that, we can now put that into our formula for the eigenvalues for this problem. And so we see that psi n is equal to root 2 sine n pi y. So let me write that down. So the eigenfunctions of this problem are psi n of y equals to root 2 sine n pi y. Okay, so with that, I can go and find out the values of the eigenenergies for this problem. So again, the functions have to satisfy this equation. And so what we need to do is to put this back into the Schrodinger equation, evaluate the left side, and find out what the derivatives are. So again, minus h bar squared over 2m times d squared psi of x dx squared must be equal to e times psi of x. Okay, so that is the Schrodinger equation right there. So now, since I've transformed to the new coordinate system y, I can again just use the new variable y to rewrite the Schrodinger equation. So remembering that the transformation of coordinates that we have right here involves this definition right here. So what we can see from this definition of y is that dy is just equal to dx divided by L. L is a constant, so the differential in y is equal to the differential in x divided by L. Or you can see L times dy is equal to dx. So now I can rewrite the Schrodinger equation, but in terms of the coordinate y instead of x, by using this relationship that L times dy is equal to is just equal to dx. So this is going to be minus h bar squared over 2m. And here I have essentially a dx squared, and that will come out to be L squared, and you have a dy squared, and you have d squared psi of y on top, and that must be equal to e times psi of y. So the Schrodinger's equation rewritten in terms of this new variable y is going to look like that. And I'm going to just group these together. 2ml squared, h bar squared on top, and this is d squared psi of y dy squared is equal to e times psi of y. And now what we can then do is to put this formula for psi n of y into this position, and then we will differentiate twice, and then we will use that to figure out what the value of E is. Okay, so let me just do the derivative without all the constants in front. So d squared dy squared psi n of y is equal to, each time I differentiate, I will get out a factor of n pi, and twice differentiating the sign will give me a negative sign, so I should get a negative in front, n pi squared, and I should get back a sine of n pi y. And of course, psi is just equal to root 2 times sine of n pi y. So I see this is equal to negative n pi squared times psi n of y. So here is a negative on the outside, so that cancels this negative. So on the left side, what I have from this equation is now h bar squared over 2ml squared. And now whichever is right there with the negative sign will give me n pi squared times psi n of y. And this is equal to En. This is for the nth eigenfunction times psi n of y. So you can easily read out what En is equal to. So En is just equal to that. So En is equal to, let me just group everything together. H bar n pi squared on top. And then in the bottom, you have 2ml squared. So these are the eigenenergies of the particle in the box problem. So far we haven't really solved the problem yet. We just basically showed that these eigenfunctions do satisfy the Schrodinger's equation, and we have shown what the eigenenergies are. Okay, so we haven't really answered the problem, but I want to talk about the particle in the box problem with sufficient detail, so you know what this is about, and actually the rest of the problem is fairly simple. Okay, so now going to the actual solution of this problem. So the question is really asking you to find the following. It's asking you about the probability of finding the particle between 1/4 L and 3/4 L. So let me go back to the original figure and draw a line indicating where these 2 points are. So let me just, this is 1/2, so this is 1/4, and this is 3/4. So the problem is really asking you, what is the probability of finding the particle between those two lines, right? And I hope you can see, but you can now see that for every eigenfunction, it's slightly different. So I think for each of these eigenfunctions, you expect to get out a different number at the end. And to see this even more clearly, so this is again 1/4 right here, and this is 3/4 of the box. So here the line goes like that, and here the line goes like that. So you can clearly see that if you integrate under these curves, the area that is bounded by these two lines is different for every one of these psi functions. So what we expect to see is that at the end, this probability of finding the particle between these 2 points will depend on what n you have for the eigenfunction. Okay, so let's just do that then. So what we want to do is to find the probability of the particle within this region that is bounded to the left by 1/4 and bounded to the right by 3/4. So you see now why I transform to this new coordinate y, because in this new coordinate y, it's dimensionless. So I can go to just 1/4, and between that and 3/4, I can just integrate over this psi function as a function of y, and I can then immediately figure out what this probability is, right? So the probability is, of course, equal to the integral of psi n y squared dy, but now the integral is between 1/4 to 3/4. And then all the L's are actually found in the coefficients in front of the sine function. So continuing this, we know that the psi function is √2 sine n pi y, and this is now squared, and I'm integrating from 1/4 to 3/4. So again, what you can do is to do this, and now you have sine n pi y squared dy. You square the √2 becomes a 2. So this is the only integral you have to do, right? And now you see that there really is no L anymore, because everything is now dimensionless. Okay, so you have to do this integral, which is a sine square. Again, you can just look up an integral table, or you can do your own sine square integration. Anyway, that's really just calculus, and that has nothing to do with the quantum mechanics. So I'm going to do it the fastest way. So let me open up a window in Mathematica. So I want to essentially just integrate this function, sine square n pi y. And so let me just define this function, psi, use small case, psi of y is equal to sine of n times pi times y. And so I'm going to integrate that. I should probably put root. Well, okay, I can leave the √2 outside, because the √2, I know the square of that is just going to give me a factor of 2. So I'm just going to essentially just integrate psi of y square from y equals to 1/4 to 3/4. Okay, so you see that's basically the solution right there. I'm going to integrate the same over the entire range, just to show you what the normalization is supposed to be. So if I integrate this from y equals to 0 to 1, it tells me that it is 1/2 minus sine 2n pi over 4n pi. So you have to understand that Mathematica isn't necessarily, it's not like a human brain. We understand that when n is equal to an integer, sine 2n pi over 4n pi will come out to be equal to 0. So now let me just copy that over. So this is equal to n pi plus sine n pi over 2 minus sine 3n pi over 2, and below you have a 4n pi, but this is multiplied by 2, so instead of 4 we only have a 2. So that's the answer to the problem. So at the end, the last part is really just doing the integral, so that's not very exciting. But the first part where I went through the reason for the eigenvalues and the eigenfunctions, I hope that's something that would be helpful, and also understanding that perhaps doing the integration is made a little simpler by transforming the variable x into a dimensionless variable y. Okay, so that's it for this video. Turned out to be a fairly long solution, but I hope it has enough details that would actually help you really dig into the heart of this particle in a box problem. Okay, so if you have enjoyed this video, please do give us a thumbs up, and also please do subscribe to the channel so that you'll be notified when there are new contents on quantum chemistry.